My name is Niu Zhaojie. I'm currently working in ByteDance data platform SE. So today I will briefly introduce our system. It's a cloud native database, and we are working on. And let's start. So this is outline. First, I will introduce some background, and then it's a design of our cloud native engine, and followed by the implementation. And the last one is some future work. Before I introduce our system, and I will first introduce the product our system is serving for, which is a ClickHouse, and it's a cloud native data analytics engine developed by us, and it's built on top of the open source database ClickHouse, focusing on improving the extensibility, stability, operability, performance, and resource utilization. And so we did architecture change on top of ClickHouse. The major one is the computer storage decoupled. And yeah, today I will introduce the system we have done. So this is the current status of the ClickHouse usage in ByteDance. And so I think we are the biggest ClickHouse users in China, and or maybe in the world. And we have this is the size of the machine, the largest cluster we have, and the data set size. And we use the ClickHouse to serving a lot of internal users in ByteDance. And there are some use cases inside ByteDance, and these four are some major use cases: user growth, A/B testing, and ads analytics, and the recommendation. Several years ago, we chose ClickHouse mining for 4 reasons. The first one is high availability, and the second one is it's easy to stand, and it's open source. Whether ClickHouse is open source, so and also its license is very friendly, so it's what everyone can extend it easily. And the third one is high scalability. So we know ClickHouse has a multi-server architecture. We don't use a master-slave architecture, so it's easier to scale the cluster. And the last one is a killer feature of ClickHouse. The performance of ClickHouse is extremely good. So these are the reasons we ByteDance choose ClickHouse for the interactive analytics internally. So this is a brief introduction of for the architecture of ClickHouse. You can see the architecture, ClickHouse using the shared routing architecture. So we can see the ClickHouse have, we can see the 4 workers in this example, and so each worker is responsible for host, computer, and the storage purpose. We can see the data is also inside each computer node, and so the compute and the storage are tightly coupled, and the data cannot be shared across different servers. So each server can only access the data inside it. So the advantage is the extreme fast in the local machine. I think recently ClickHouse released a ClickBench with a benchmark, and you can check in their website, and its performance is especially for the single table query, and it's the fastest one. And there is some disadvantage for this architecture, the compute and the storage cannot be scaled independently because we see the data inside the computer node. So the compute and the storage cannot scale independently. So which leads to the bad elasticity. And the second advantage for this architecture is the data cannot be shared. Then even we want to add more machines, and if we don't balance the data, then the newly added machine can still not be used for computing unless you move the data to those new machines. So this is an example to show the problem on scaling. And so we can see the inside ByteDance it's also a real story, a real requirement internally. The application is expanding extremely fast, and so the different team has strong requirement on cluster scaling. For example, if one class 2, when the class 2 want to use more resources, and maybe it's the class 1 don't need so many resources, then the class 2 can borrow some computer nodes from class 1. So we can see we can simply move the server to this the class 2. However, it's not that so easy because the data is also inside this 2 machine. So before moving to this class 2, we need to move the original data back to the remaining machine of class 1. And then after that, we can move to the new cluster. But after moving, we still need to balance the original data in class 2 to these new servers being borrowed from the class 1. After that, we can start to use these new resources. So we can see the migration cost is very high on this shared nothing architecture. So the idea is very straightforward. Then we just share the data, and that after we have this idea, then we start to design and implement our new systems. So basically, you can see this diagram, and we just connect the 4 nodes share. We just decouple the storage from this computer node. Then every computer node can share the data and read from remotely. Then it's easy, right? And the problem solves. Then we start to explore this new architecture. We made some design and finished the implementation in the past 2 years. So this is an overview of our engine. You can see on the bottom is storage. We can utilize many well-known distributed file system or object store for the data storage, like HDFS, Amazon S3. Then on top is in order to adapt different storage backend, we have abstraction on this data storage layer, and we call it virtual file system. Then on top of this abstraction, then it's our computing resource. So you can see we can split the computing resource by virtual groups, and each user can have their own computing resources. Then you guarantee to get the isolation from the physical level, and also if everyone, each user wants to scale their class warehouse, they can just apply more machine and adding into this pool, and so the computing resource can be scaled on demand. It's not related. It can be scaled independently from the S3 or from the storage layer. So this is an overview of our new engine. So the advantage is it achieves better elasticity and scalability, like I said. However, there is no silver bullet. Then it also has its disadvantage. So it has extremely high latency for remote access. For example, compared to the local read, you read from HDFS or read from S3, then it will be read from the S3 will be much slower than read local. So this is a disadvantage. And later I will introduce how what we have done to fill this gap. And this is a component of our engine. Basically, we can focus on these two, the server and the worker. This is the computing resource. And so for the computing resource, we can further split them to read workers, the read resource and the write resource. So we can separate the read and the write. The write will not impact the read. And for ClickHouse, then it will be more interesting, like for the background task like the merge, we can also run in the write worker, then it will not impact the read performance the user varies most. So after we did this disaggregation architecture refactoring, we benefit we gain a lot. Like we can separate the read and the write. Before we know for the ClickHouse, the read and the write are all go through the same node. Then the read sometimes will be impacted by the heavy write. And the other part we can focus on is storage. So for the data, for the storage, we have two kinds of data, the metadata and the data. And for the metadata, we store it in a distributed p-value store. And for the data, we can utilize S3 or HDFS directly. So we don't need to worry a lot about the storage, like replication, something like that. And then let's take a look how do we implement our new engines. So I will use two simple examples to show it. The select, query, and insert, the read and the write flows. So for the read, and if you are familiar with ClickHouse, before we read the data, the first thing we need to do is we will get the metadata, which is part in ClickHouse, and we will first get the metadata from the catalog, and then we will distribute those metadata to the virtual warehouse, which is a computing resource of our system. And after that, our computing workers will read the part from the VFS, which from S3 or HDFS and perform the computing, and return the result back to the server and finally to the client. So the flow is quite easy. And also for the write, the insert, and it's the reverse process of the read. First, when the server, the client just send the select, the insert is equal to the write worker. And then the write worker will write the data to the remote file system. And after that, it will commit the metadata back to the catalog. So this is two simple examples to show how the read and the write works inside our system. So let's have a review for the new architecture, the disaggregated computing and the storage architecture. And the first one challenging we met is we have the performance degradation caused by the remote data accessing. So how should we solve it? The first one is, so we consider the hardware and software co-design. First one is we relying on the development of the modern hardware, like the high bandwidth and high speed network. And this is also a trend. And the other one is we done a lot of work for the data and the metadata cache in our system. And the second challenging we met is before we know that each worker will be responsible for the data inside that worker. But now, after the separation, then the data will be stored remotely for both the data and the metadata. So we need a distributed data management for this two kind of data. So for the data itself, it's simple. We just rely on the existing file system or object store to handle all of the issues. We don't need to worry about it. Like in a public cloud, we will directly use S3. And for the metadata, where it will be a little more difficult because we need to handle some like the some, because it's also a distributed environment. We also need to handle some transaction schematics for this kind of metadata. And let's go through these two challenges one by one. The first one is we leverage the cache to fill the performance gap. For the query, we try to catch the data, hot data as much as possible. Like for the metadata cache, like the table and the part, we will have the cache for these two objects in our server, and also they are in memory. And for the data, and we for the part data of our system, we will catch them in the computing node, which is a worker in our system. And we also have the hierarchical architecture for those data cache, like the disk and the memory. So after we've done this, we can achieve similar performance as ClickHouse, but it still have some gap. Like we can control it on the for about 10%, because we still have some metadata allocation cost. And so for this part, we so because of this, we still have a little bit of gap for teaching our system and the ClickHouse. Then the second challenging is for the distributed data management. Then for the data itself, we can directly use existing file system to support it. For the metadata management, we implement a transaction layer for it. And let's take a look at how it works on it. And so because we can see from this diagram, with if you are familiar with ClickHouse, then you will know, for example, when you insert the data, and the data will be right block by block. So you consider it's like a read stream, and you wait for a batch is full, and you do a down, and so it will split the blocks to the parts, and then the parts will be down to the file system, and the metadata of those parts will write to our catalog. And so our catalog is, you can also imagine it's a distributed database, because the metadata is also very huge for our system. So we still need to use multiple nodes to store those part of metadata. And so which means we need to have the distributed transaction support on it. And we guarantee the ACID properties for the metadata management. For example, when you insert huge of data, and you will not see the partial data until the whole select finish. And also at the same time, if the query finish at the middle, then our transaction model will automatically roll back and delete the garbage data left in the system. And for our system, we also need to handle the concurrency read and write case. For the concurrent write, we just simply use the lock, and we provide the lock at different layers. And for the concurrent read and write, in order to minimize the mutual impact, we develop a multi-version management for our metadata. And so we will not do for each update, we will do the in-place update on the part. Like even you add a column, you will create a new part with that only contains that columns for this adding column operation. So the read, so the old data is still there. The current reading can still use the data without impacted by write also at the same time. So after done this, we can achieve better performance under the concurrent read and write scenario. Yeah, because the time is limited today, I just give a brief introduction of our system, and in future we will have more sharing, deep dive into. We can split our system to different modules and organize some series to go into more details for each component in our system. But in the short, recently, we are consider these three scenarios in our inside. Like so we will support the smarter data catching policy, and the second one is we will improve the indexing, our indexing service. Currently, our indexing is for each part. We don't have the table level and the indexing, and also the indexing itself is for each worker, but we don't have a unified indexing service for the whole system. So this is another part we plan to explore. And the last one is we also have the plan to support the open source data lake protocol like Iceberg and Delta Lake, and the proposed by Databricks. So after we have this support, then you can also access the data in those data lakes. Yeah, I think that's all for my sharing. And if you are interested in ByteDance, then you can take a look at our white paper and this book. And also, you can also access the ByteDance website to try it. We should have a free trial for everyone. And the last one is we are still hiring, and if you have a passion on working on the distributed system and the database, you can contact me through this email. And you can also find me offline here after today's sharing.
We still have 5 minutes to go. Do you take any questions like Q&A sessions? Do you have that?
Yeah, sure. If you have questions.
Any questions for Niu Zhaojie? Actually, I want to ask, like, is it the computation layer? Is it still as the house, or do you have something changed?
The computation layer, not too much. For the SQL, we have two parts. We also support the distributed query plan. That part we have done a lot of work, but for the SQL, this part we try to keep the existing ClickHouse execution model.
For the SQL, what part?
Like the processor models.
Oh, okay. So support like the distribute plan. So it means like the engine can shuffle data around for like compute job.
Yeah, support the real MPP, and we also for that part we did a lot of changes.